Hello, so my name is Jordan Nguyen, and I've been in Terabats for 1 year.
Hi, I'm Nithin, Lokesh, and I've been in TerraSpeak for about 4 years now. And today we're going to be doing a interview with Dr. Tyler Curtis and his career path in systems engineering. So, Dr. Tyler Curtis.
Hi, so my name's Dr. Tyler Curtis. I'll be presenting today on systems engineering career path, and specifically about some of the education, some of the pathways that I took to get into this career. So first, quick disclaimer before getting in. The thoughts and ideas presented here are solely my own and represent my own experiences. And they're in no way intended to be representative of the thoughts and or ideals of Michigan Technological University, the University of Notre Dame, or GE Healthcare. So with that out of the way, my background is that I went to undergraduate studies at Michigan Technological University, where I majored in bioengineering with a focus on tissue engineering and material science. After that, I did a 5-year program, doctoral program at the University of Notre Dame, where I studied bioengineering under the aerospace and mechanical engineering program. And from 2019 to present, I'm currently working as an image quality / systems engineer at GE Healthcare. So I guess the first question is, what is bioengineering? So bioengineering is a very interdisciplinary educational path within the engineering sciences. And it really came into focus in, I'd say, the early 2000s, where there was a lot more of this discussion of how do we treat complex healthcare problems in a manner that can address both a quality healthcare solution as well as communicate efficiently amongst these engineering fields and bring multiple fields together to come up with these solutions. So in that regard, as a bioengineer, I studied biology, material science, electrical engineering, anatomy, computer science, chemistry, mechanical engineering, math, and physics during my undergraduate studies. And specifically, as one that wanted to focus in tissue engineering, I tried to focus my studies primarily on biology, material science, anatomy, chemistry, and math. And I really wanted to focus on tissue engineering because at the time it was touted as a method for some very advanced healthcare solutions. I, for instance, have type 1 diabetes, and so one of the primary cure solutions, or sort of cure solutions, was come with a methodology for creating nanospheres that would contain beta cells, which would be protected and allow you to produce insulin as a type 1 diabetic. So I became very interested in those kinds of studies, but I didn't really know what kind of career path was actually available to tissue engineering. So a lot of these solutions were all within research space, and not many were making it to a market solution. But I was really interested in becoming an expert in the field. And so with that in mind, I joined an undergraduate research program at Michigan Tech under Dr. Nithin. That study looked at nitric oxide releasing polymeric biomaterials. These are basically polymers, so coating materials that are made of carbon chains with many different attachments or secondary atoms on them, allow for the protection against biological interactions while within the body. So what the intention was to take these coating materials and put them on implanted biosensors. For instance, for diabetics have currently these continuous glucose monitors, which have a small needle which injects underneath the skin, and they maintain a sensitivity to glucose for a period of about 2 weeks. And the intention behind this research was you coat a material like that in these polymers, and they'd be permissive to glucose coming through these polymers while reducing the amount of coagulation and interaction that happens on top of that copper pipe. So nitric oxide is used to reduce coagulation and extend infinite life. The idea was that these polymers would be developed in a way that would allow them to release nitric oxide over the period of their life in the body. Nitric oxide can also be used to sterilize medical equipment, and a secondary portion of this research was looking at using this as a sterilization method for other inputs in the body. So I gathered a lot of tissue engineering knowledge and a lot of just general anatomical knowledge from this research program. While at Michigan Tech, I applied for a summer undergraduate research fellowship at Mayo Clinic in Rochester, Minnesota. At the time, I was scheduled to work with Dr. Romero, which the research involved genetically engineering Drosophila flies for large-scale investigations of nephrolithiasis. Basically just means we were taking fruit flies and we were giving them kidney stones. And this was done so that that professor could understand and tweak different genetic markers within these flies and do high-scale studies of what the impact of these changes to different genomes that were associated with kidney disease had an impact on end-stage kidney stone development. And Drosophila flies were picked out because they have these small structures within them called Malpighian tubules, which are very similar to the structures that we found in kidneys. And so this allowed a high throughput method to quickly analyze many different variations on genetic markers to see when these kidneys develop. Fortunately, that didn't work out. While I was scheduled to work with Dr. Romero, some logistics fell through and I wasn't able to work with him throughout that program. But in the meantime, Dr. Romero had set up Dr. Whitman and gotten me into a different program at Summer Undergraduate Research Fellowship. This study was actually looking at taking those slides that Dr. Romero was developing and doing dual energy and micro CT as a high throughput imaging modality to evaluate the genetically engineered Drosophila flies or nephrolithiasis. So I'd gone from looking at biology, material science, anatomy, to switching over to computer science, electrical engineering, math, physics, which was a big change up in the program. But we took it with stride, and from this project, we actually looked at taking what we call desktop CT, so these would be experimental CAT scans. So very similar to what you would see in a clinic, where a patient may go in, get an X-ray exposure and get a 3D image from that X-ray exposure. So what we were doing was taking many of these fruit flies, and we would scan them with this micro CT. And so what happened was when we scanned the CT is we take an X-ray spoilers. On this rotating stage, we attached, basically it was a small plastic film with many little Drosophila flies attached to them. And behind that rotating stage is a simulator, which is a crystal that takes the X-ray source and converts it to visible light photons, which can be actually absorbed by the detector and registered as a signal for the detector. So we fire X-ray, simulator absorbs the X-ray source and expands the number of photons, and it's registered in the detector. The next step we would do is we would take the same X-ray source, we would replace the X-ray tube, which allows us to go to a higher KBP. And then we would fire this higher KBP at that sample of flies again and get another registration. And so this would give us two separate images for the same sample of flies. And so this was important because what we were trying to do was identify the small calcifications that were indicative of kidney stones within the body. So in conventional CT, you have materials, you have the X-ray source, you go through your object, and it hits the detector. Traditionally, an object has an attenuation curve that is correspondent to the photon, the energy of the photon coming into the object. So that's a complicated way to say that basically anything that you're looking at will absorb photons in an energy dependent manner. And so with traditional and conventional CT, what you do is you get one exposure. So the image that you look at will cover this entire photon range. And so in the end image, you just get one grayscale value for every material that you're looking at. So you can tell, it's basically like looking at a black and white image on the screen. You can tell that there are different objects and they have different densities. You can't tell really what those objects are made out of. And so with dual energy CT, which is what we were using for this Drosophila fly study, you get two energy source different cancer types. So I was able to show that with this photon counting CT that you were able to actually separate out material. You can see that in the original image, you have areas where you have cobalt ions, calcium, gadolinium, iodine. Once you run it through material decomposition, you can run it into different locations and show that you can separate out the calcium, gadolinium, and iodine into their own separate channels, even when they are within the same local area within the image. And further this study, I looked into elemental decomposition. This will take one step further, where the previous materials that we've shown in the mixed composition have did not use, which is a distinct energy spike, or a distinct attenuation spike at specific energy. Many materials that are found locally within bodies, such as calcium, phosphorus, or magnesium, don't have these typical attenuation spikes, which can make them harder to identify. So the next study that I looked into was looking at separating out calcium and phosphorus. And this was important because different pathologies have a association with different types of calcium microcrystals, which contain different compositions of calcium and phosphorus. One of the ones that we were most interested in was identifying benign versus cancerous associated breast microcalcification in association with breast cancer. And they have two distinct groupings, which are calcium oxalate and hydroxyapatite, which the calcium oxalate has no phosphorus in it, while the hydroxyapatite has some amount of phosphorus in it. So in this brief study, I looked at combining calcium and phosphorus in different combinations within tubes, running the material decomposition, and was able to show that you could actually separate out calcium and phosphorus that was also full. And this was done by taking advantage of the knowledge that I gained over looking at these attenuation profiles and trying to simulate and maximize the separation between these signals. So I'm running multiple simulations and come up with a field composition scheme that allows you to separate not only hydroxyapatite, but also just separate out the calcium and phosphorus specifically within those crystals. And this is showing that because of this, you can look at different ratios between phosphorus and calcium and use that ratio to identify specifically which type of calcium microcrystal you're actually looking at in the body. So this is just showing two different approaches that achieve basically the same result between looking at an isovolume and a true volume material calcium phosphorus. So they were very long studies that basically just showed that if you could get down to a very specific weighting between phosphorus and calcium, you get math that we have as the phosphorus to calcium to phosphorus ratio, which you can see if you look at the left map, we have calcium oxalate at the right corner. On the far right, we have dicalcium phosphate, which is a different composition of calcium, and hydroxyapatite, which is our indicative crystal of that would be indicative of a cancerous breast calcification. And you can see when you look at the individual elemental compositions, they have it's hard to distinguish between these different groupings. When you look at the phosphorus and calcium, you can see that regardless of the concentration of the material that you're looking at, you can see the signal levels normalize and you can separate out different groupings by just thresholding out which level of calcium phosphorus location is. So it's a long way to say it worked this time, and what I learned was about clinical applications and clinical motivations within CT. Also some of the business motivations, because I had worked with specifically a startup company that was developing this technology. I also learned about data management, because a lot of these files were quite large compared to standard practice CT files that are stored in DICOM, which and a lot of efficient programming to ensure that while all these steps be processed at a certain pacing, to get done with the project in time, I had to come up with some advances within the programming language I was working in to make it work fast enough to actually get the results that I wanted in a time. I also practiced in team communication. Again, a lot of interactions between clinical researchers as well and electrical engineers and this small company as far as getting this project to work and coming up with a design that was not only effective in identifying and showing the applications of technology, but also in a use case that would be clinically relevant. And through this, I again practiced more project and experimental design, and hence, as with a lot of doctoral research, a lot of presentation and support writing. So what I do today is I'm an IQ engineer. I've been working in this field since 2019 in image quality and systems engineering at GE Healthcare. I work primarily on the premium computed tomography and line of products, which is, say, our high-end computed tomography. So this is in our X-ray CT line of products. So as an image quality engineer, I assess the image quality of the product. I've been tasked with identifying improvement opportunities for the images by looking at different images across different acquisitions from different sites and determining like the root cause of an error or an artifact within the image. And this may lead to the development of software or hardware features to address the perceived IQ issue that a site is seeing, or alternatively, there may be like a procedural or operational issue causing error, which is where the system engineer side of the project would actually come in. So as an IQ engineer, and I'll highlight, this is not from any of the GE CT systems. This is just a CT image that I pulled up from Wikipedia. But what we would do in this case is you might get a complaint of an IQ issue with this image. So this image is of subarachnoid hemorrhage. And what they may flag as an issue here is, for instance, they have quite a large white spot in the center of the image here. And so that could be either related to an actual anatomical feature that's held within the patient's brain, or likely is a center artifact smudge, which is, say, based on the reconstruction or the kernel that they were using for reconstruction. It may cause smudging or image blurring, which can be confused with anatomical features. So an all-2 engineer would go in, look at this smudge, and then look through the image chain, test different features of the image chain to see what enhances or removes that smudge, and then recommend that change to either the image chain or the procedural evaluation to improve this site's IQ. So as an IQ engineer, I've had to rely on my knowledge of anatomy, again, for more computer science, math, and physics. And for the most part, I've taken in this field, I've had to apply some basic skills within Linux. Linux has actually been very important because a lot of the programming that we do within the CT area is all programmed up within a Linux-based OS. I've had to do a lot of report writing and statistics, which are very important in communicating these ideas. It's really no good if you are able to identify these issues, but not able to quickly and efficiently explain what the issues are or how to fix it. I've also had to continuously update experimental design and show how that experimental design is actually proving that these are the root causes of the image quality issues that we're seeing. We've also used simulation, in which case we take inputs from a site and they simulate the same image on one of our engineering systems and input fluctuations within that simulation so you can achieve the same artifact that the patient may have seen. I've also had to apply some of my material decomposition knowledge because a lot of our premium CT lines focus on either doing material decomposition through a dual energy system interface or through photon counting CT, which is really coming the next line of systems that GE is working on. So with all that, I've also worked as a systems engineer, and a systems engineer is really responsible for the system level view of product. We work with multiple subsystems on feature implementation. A feature can be anything from procedural update, a new hardware implementation, software on the system that will enable new features for different image analysis or different modes of reconstruction. In the same, we work closely with the IQ and service teams on procedures and different documents and system designs while we develop these new features on the system. So as a systems engineer, you have to focus a lot more on the overall interaction of the entire interface. So on the console side, which is actually used to control gantry, you may have to develop user interfaces, data storage interactions, image renders, system control software, basically anything that the user will wind up using for interacting with the system. You have to consider then also how all of these interfaces you're building on the system are interacting with the gantry and interacting with the personnel that are using these interfaces. On the personnel side, we also come up with procedures and training for using the interfaces and to take feedback from the personnel to see if we can do any improvements for these interfaces on console or anything on the system as far as maintaining control or sending feedback from the system indicating errors are actually occurring. So this really delves into the usability of the product, a lot of documentation and maintenance of the system. So we have to consider the entire life cycle of when coming up with these procedures too. So for the gantry, we are concerned with the subsystems that are actually used to maintain the quality of the image. So a lot of things that we have to consider are the thermal management of the system, because the particular interface will respond differently depending on different temperatures that it's looking at. Data transfer coming off the system, the file size, and how we actually represent that data coming from the gantry, going back to console, table control, rotor control, things that basically control when the patient comes into the field of view, how fast that gantry is actually spinning to acquire different imaging modalities. For instance, we increase the speed at which the gantry moves from a 1 second per revolution to a 0.23 seconds per revolution, which for cardiac scans, and this is to achieve a full image in between the beating of a heart while a patient is actually on system. And for instance, with that project, we had to come up with a lot of different subsystem interactions to allow the rotor or the gantry to actually spin that fast, because the gantry is actually producing at 0.234 about 70, I think it's about 70 Gs of force coming off the gantry. And for instance, when a rocket is coming off into space, the force that the astronauts are feeling while they're lifting off is max, I think, about 7 to 8 Gs. So we're producing about 5 to 10 times the amount of force on all these mechanical parts that run through the system when we're applying this 0.24 rotor or gantry speed. So there's a lot of interactions that we have to consider when we develop a feature like that, which really involves us communicating a lot with a wide variety of subsystems that come running. So overall, as a systems engineer, most of what I deal with is computer science, as far as simulation and my day-to-day work. But a lot of it is communication, documentation, and control. It's key to being an effective systems engineer. But that's not to say that all the skills that I gained as a bioengineer are wasted in a systems engineer. The major advantage of coming out of the bioengineering background is being able to consume the information from multiple engineering subsystems and communicate that information across multiple team perspectives. So while I may not be applying anatomy or computer science or mechanical engineering every day, I am able to communicate with all of the engineers across the thermal team, across the gantry team, across detectors for physics and math, and relate that back to our other subsystems and able to communicate between these different teams effectively in order to develop these different features and things that we deal with on. So with all that, that's really what I do day to day. And I guess all I have left is if you have any questions for me.
Yeah, for sure. That was a great presentation. Something that I thought like students might be interested in is what skills, because I know bioengineering is very interdisciplinary, right? There's a lot of different ways you can go about a bioengineering major. But what skills do you think are important for students, especially in like high school, to like develop if they wanted to go into like the same type of career path that you went into?
I mean, so I think the most important skill that I've learned over time is the ability to communicate with, basically communicate with people and understanding what their actual end needs are. So if you want to go into, I think, any engineering career path, you have to be able to communicate with your end consumer. So we'll say, like in systems engineering, we'll say our end consumer is maybe the clinical site that they're trying to develop some sort of imaging modality that they're trying to scan very quickly, or they're trying to see new small structures or whatever. You have to be able to understand what their end goal is and how you can actually deliver that effectively. So a lot of it is communication. I think that is probably one of the biggest skills that a lot of engineers lack, but it is kind of key to the role that they're getting into. I shouldn't say a lot of engineers lack, but some engineers lack.
So a question I have is going into the bioengineering field, how competitive was it? So for say aspiring bioengineering people that want to go into this career path, how competitive do you think it would be, and how hard would they have to work?
I mean, it depends. So bioengineering has a lot of, you gain a lot of different skills going across that field. So I have colleagues that have come out of both undergrad and grad school that have worked in everything from research at the NIH to small startups at working within AI to, you know, doing what I had originally intended to do, doing actual tissue engineering. I think the fields are competitive, but there's a lot of diversity that you gain by going through bioengineering that makes it a lot easier to jump from one section of engineering to another. So as long as you are open to change, bioengineering is actually a very good career path so that you can gain those skills to be able to switch between different areas throughout your career.
Another question that I thought would be pretty interesting is like if you're going through like a doctorate program, there's definitely a lot of like networking involved, right? Like kind of making connections. What would you say was kind of like your path to kind of getting in like contact with these types of programs and kind of like getting, because a lot of your experiences that are helping you today was because of these previous programs. What would you say helped you, and what do you think would help others kind of get into these programs that would help them in their future careers?
Yeah, so a lot of that was, so for instance, for that first research group that I had joined, I had done that because I had taken the initiative and joined the lab very early on while I was in undergrad. So part of that was because I had known that I was interested in doing research, and Michigan Tech had a very open policy for undergraduates starting within that research field. Some universities don't, but stepping up with your professors and kind of showing your interest in the research that they're working in, or if you're in a university and you want to get involved with that kind of research, having like a good knowledge base of what the professors at your university are doing and showing interest in those career paths, or maybe not career paths, but those projects, can actually help a lot with opening doors for communicating out past that area. For instance, part of the reason I got into the CERF program was because 2 or 3 of my professors that I was working with in undergrad had knowledge of the CERF program and had worked collaboratively with some of those professors in the past. So I had a small advantage in getting into the CERF program in the first place. So it's one of those things where it's small acts and small measures of showing initiative with your professors that can really set up doors that can open up to new opportunities in the future.
So a question I have is, what would you say to aspiring bioengineers who would initially, let's say, fail a project and they would maybe feel a bit low? What would you say? What is a learning experience that could help them strive for maybe a more successful project?
Yeah, so I think it's very, I can understand how it can be very hard to receive the news that your project didn't work out or it wasn't a good project. But I feel like what a lot of people miss out is that there's a lot of things that just don't work out in science. You're doing these things to investigate and try to come up with something new, and not all of them are going to work out. But what an engineer or somebody studying within these fields should take from these things is, what skills did you actually learn while you were doing this? For instance, like I said, that first Drosophila fly project I did at CERT didn't work out at all. It wasn't feasible for the resolution that we were looking at. We had hopes that it might be doable for this project, but after all that, I had picked up a whole bunch of skills that I didn't know were going to be useful. That turned out to be like vital for my products in the future. So just doing like a small retrospective for yourself and appreciating what you actually learned from these projects, I think is very helpful.
Yeah, more on the idea of because for example for you your paths have been so diverse, right? There's been just so many things that have happened. But if you had to say one thing that you kind of go back and change, or something that you would do differently now that you have this knowledge, what would that be? And what would you advise future students to also do differently?
I had to go back and do anything differently. If I'm being honest, I couldn't choose to do anything differently because I'm pretty happy with where I am in life, to tell you the truth. But if I could avoid some of the hardships going through, I would say that the first thing I would do is really evaluate what groups I'm joining and trying to make sure that I'm using that time effectively. There were periods in my undergraduate career where I had joined labs or I had done projects that were more on the interesting side than career focused. And while I would like to tell you that those were not the projects that you should do, I think that I would actually say I should have done more projects like that and tried to get in a lot more joy or more interest in those projects moving forward, because there's a lot of those things where somebody will tell you that those projects are goofy or they're not going to teach you what you need to do for engineering. But you can always learn new engineering skills even in those kind of one-off projects. I don't know if that made sense, but that's what I have.
So the final question for me is, how was so going back on the experience, is how was your experience with maybe lab partners, and have you learned maybe communication skills that you may have not had previously?
Yeah, I think as a young engineer, I became very frustrated with lab partners quickly because I may not have understood everything that they were going through at that stage in their life or the pressures they were under at that time. And I think I had overweighted how important some of these projects were. So I think growing older, I've learned to communicate more effectively in a way that's more healthy about trying to get projects done, and coming from a perspective that is more understanding towards other engineers or towards other perspectives on projects. So, like I was saying, like while an engineer might come up with a certain solution, it might not be exactly what the final product actually wants. And being a little more understanding, a little more open in your communication and empathetic, I think is very important in those communication skills.
All right, yeah. For most part, that was our final question. Thank you so much for having this presentation. And yeah, if there's any like final thoughts that you had that you wanted to leave off with, feel free to share that. But yeah, that's pretty much all from.
I think I've given you all everything that I can, honestly, to tell you the truth. So I hope it was worthwhile for you guys, and I hope you learned something from it. So.
All right, yeah. Thank you so much for joining us today,
Thank you.
Dr. Curtis. Right.
Okay.
Bye.
Bye.